In order to prove this star equation, we'll start with both sides simultaneously. This is the left-hand side and this is the right-hand side. And one idea is to turn those products of integrals into iterated integrals. And somewhere we need to use the Fubini's theorem. So let's try it. The left-hand side is equal to, let's put the variable x and y into the integral. And we'll force this guy to be an iterated integral. I will leave this part alone for a while, because at this moment, we don't know how to proceed with this last line. So let's turn to look at the right-hand side. We'll do the same thing. First, we'll add the variables and combine this product into one iterated integral. At this point, if there's anything we could do, maybe we could switch f and h. So let's switch it on the left-hand side. We put h in the front and f behind. So you see the integrand of left-hand side and right-hand side are pretty similar to each other, except for the rows of x and y. And our next goal is try to turn the right-hand side into left-hand side. We'll try to turn this h of x into h of y, while making some necessary change to this part. Of course, you can imagine we're going to use the Fubini's theorem and the left invariance of measures, things like that. First, let us use the left invariance of mu. So by the left invariance of mu, we have this integral is equal to h of y inverse x times f of y d mu x d nu y. So here we're using the left invariance of mu in its functional form. You can think of this as L sub y inverse applied to h, acting on x. Actually, you know what? In the existence proof part, we start with the invariance of functionals, and only later on we move to the invariance of measures. So actually, the invariance of the functional is something we got before we can even prove the invariance of measures. So this part should be something that looks more natural to you, considering the order of steps we use to prove our existence of the left invariant measures. And now we're going to use the symmetry of h. Remember, by the symmetry of h, we have h of x is always equal to h of x inverse by our construction. This is how we picked our h up here. So we're going to replace this guy by x inverse y by taking the inverse. And now, next, we're going to use the Fubini's theorem. The motivation for us to use the Fubini theorem is that we can see that in the integrand, y appeared twice in two functions, but x only appeared once. So we want to integrate this guy by first integrate it against nu y and then mu x. That is a more natural step. So by the Fubini theorem, or Tonelli, Fubini-Tonelli, we can switch the order of integration. So this will become, the integrand is the same, but we'll first integrate against nu y and then mu x. Next, we're going to make a small change to this part. We want to simplify the argument for h and make the argument for f more complicated, because as I mentioned to you earlier, we want to make this part be equal to h of y so that we can compare left hand side and right hand side. So let us make a little transformation. We turn this to f of x inverse times x times y d nu y d mu x. And now you know what we are going to do here now. We're going to use the left invariance of nu to remove x inverse from both arguments. So here we're going to use the left invariance of nu. And this will help us take off x inverse and x inverse here. And now you can see the right hand side looks very similar to the left hand side in the last line, except for the order of the integration here. So our next step will be to use the Fubini-Tonelli again to switch the order of integration. So now let's apply the Fubini-Tonelli again. This gives us the integration of the right hand side that is in the same order as in the left hand side. Now they look very much similar to each other now. The only difference is that here for this f, on the left hand side we get f of x, but on the right hand side it is f of xy. At this point, it seems to us that we are very close to proving that they are equal. We seem to be just a couple of steps away from the final success. However, at this point, I would like to warn you of some sloppiness in our proof. We are a little bit sloppy in some steps in the proof here. Do you see where? I'll let you think about it for a while, and I will tell the answer. The places where we were sloppy are the places where we applied the Fubini-Tonelli theorem, namely this place and this place. Do you see why we were sloppy in those two places? If you don't see it, just open any book from real analysis and turn to the page for Fubini-Tonelli theorem and see what things are missing in here. I'll tell you the answer anyway later. The subtleties are the following. Remember, to apply Fubini-Tonelli theorem, we need the measures to be sigma finite. We can use Fubini-Tonelli theorem here, not because mu and nu are sigma finite on G. As a matter of fact, we do not know whether they are sigma finite or not. If you don't remember the statement of Fubini-Tonelli theorem, let me remind you. You can find this in full-length real analysis, page 67, section 2.37. You can find it in here. So it's not because mu and nu here are sigma finite on G, but because F and H are in the space of compact supported positive functions. So we can restrict the domain of integration to compact subsets and use the fact that mu and nu are random. Random measures are finite on compact subsets. We have already shown that mu and nu are random from the proof of the existence using the Riesz Representation theorem. So mu and nu are finite on the compact subsets, just by definition of random measures. And now we can safely apply the Fubini-Tonelli theorem. However, to be rigorous, let's still look at, in our specific situation, how this issue was addressed. So here, F and H are both compactly supportive functions. They're all functions from CC plus of G. So F and G do not vanish only on the compact domain. Namely, in order to make F not vanishing, Y can only take a value from a compact set. And to make this H non-vanishing, X inverse Y can only take values in the compact set. So for this situation, Y can only take values in a compact set which is a support of F, and X inverse Y must be in the support of H. Or in other words, X inverse must be in the support of H times Y inverse. And because Y is in this compact set, so X inverse must be in the support of H times the inverse of the support of F. Or if you take the inverse of both sides, x must be in the support of f times the support of h inverse. But anyways, this part is again compact. Because the inverse of a compact set in the topological group is again compact, and so is the product of two compact sets, because the inverse map and the product map are both continuous, and the image of compact sets and their continuous maps are again compact. So this guy is compact. So we can restrict the domain of this integration on the compact subset of the product space. And apply the Fubini-Tonelli on that compact space. And this compact subset is actually the product of this compact set and this compact set. And mu and nu will be finite measures on those two compact subsets, respectively. But they are random measures, and in particular, finite on those compact subsets, respectively. So we can apply the Fubini-Tonelli theorem safely. Same for the situation number 2. And this addresses the subtleties in here. With the resolution of the issue of applying Fubini-Tonelli theorem, let us go back to this previous page and look at what's going on in the last line for the left-hand side and the right-hand side. As I mentioned to you earlier, in the end, we got left-hand side really similar to the right-hand side. And the only difference is this part. And now, if we add an additional hypothesis, that mu is bi-invariant, namely, mu is also right invariant. This is the case if the group G is abelian. If the group G is abelian, then any Haar measure is bi-invariant. If we have this additional hypothesis, then if you look at the last line of the left-hand side, which is equal to, since this h of y is a constant, if we consider the inner integral and use the, now we have the right invariance of mu. If we use the right invariance of mu here, we can see that this integral is equal to this one. This is by the additional hypothesis that mu is right invariant. But what is this? This is precisely equal to the right-hand side. What we got in here. So, with this additional hypothesis, we proved the left-hand side is equal to the right-hand side. As a result, we got the uniqueness of Haar measures up to a scalar.